So the next section that we're going to do, I'm just going to switch this up real quick. Matt is going to cover a bunch of airflow stuff. So it's we're going to talk a little bit about ducts. I'm going to just kind of sit up here and I'm just going to kind of comment as we go. But we're going to talk specifically about a bunch of airflow ducting related stuff.
So I thought we'd start with, I know we've touched a little bit on it. Brian talked about what is a manometer and how does it work. Just a quick show of hands, how many of you guys have a manometer? Okay, almost everybody. How many of you guys use it regularly? Okay,
every day.
Yeah.
You guys have been through NCI training, right? Who here has been through some NCI training? Some of it. Okay. I want to quickly just take as a quick poll, like, what are your thoughts about what you received from NCI training and what do you apply? Just a couple of you.
We've seen a lot of improvement since we've done the duct optimization diagnostic performance testing.
Okay.
So it's now in the forefront of our mind. We're looking at
Good.
how the systems perform.
Anyone else? Kieran, were you going to say anything? All right, Jerry?
The main thing I use, we got a lot of it. I really just go down to 2 pages for the bulk of what I use out of it. It's where it tells you the filter, helps you size that better, and then the page right before it tells you your round duct and the CFM that should go with that.
Right.
That gets you through a lot of problems, just those 2 things.
Yep.
What was the second part? The roundup to the CFM?
The flex duct.
Oh, okay,
how much CFM you should put through a flex duct.
The sizing of the flex ducts?
Yeah, so and the only reason I want to say that is because I'm really buddies with those guys. We actually talked to them beforehand to tell them we were coming down, and they offered to let us use anything that they have and all that. But I want to say that what we're going to say here is is not in contrast to that. It's in addition to that, right? So we're not going to focus on a lot of the same things. Because we knew that you already had that piece. Anyway.
Yeah, that's the way deeper dive. And you can take those classes. I believe a lot of them you can do online if you really want to get into this. This is more like
We were waiting when we bring that for you. We came up better, so we don't tell them.
Yeah. I'm just upset that you were even weighing it. That was even a question. You know what I'm saying? Like, that kind of hurts.
Why'd you tell us that?
Bruner was telling me, he was thinking about doing another NCI, and I just told him, why not Brian? And then, here we go.
There
you go.
is.
Well,
Yeah.
thank you.
Yeah. So I guess I'll just say this. For me, airflow has kind of been, it's one of those pieces that I think is the hardest to do anything about. That's been my experience. What's been y'all's experience? Is this something? So you go out and you test static pressure. Like, where do you go from there? You know, what's?
Yeah. I mean, I find it difficult because I'm on the sales side now. But when you try to do a upgrade, it's very complicated and expensive. It's not straightforward. It's not just a simple change the condenser. It's got to redesign, got to reconvince them, and they've lived in the house for 30 years. They don't understand why the neck grills always rattle. It doesn't make a difference to me. That's kind of the harder upsell sometimes. Less than strong.
Yeah.
The question kind of is there a problem with the homeowner cares for? I mean, are they having failed lawnmowers? Do they have everywhere it's a lot of rooms that are not cooling out? They're complaining about it.
Whistling.
It's always whistling. Yeah. So you might have people that complain about things, but a lot of times the solutions are expand. This has been my experience anyway. They're really expansive, and then they're like, I think I can live with that, right? So to me, putting this airflow piece together, there's kind of been 2 aspects of it. One, it's like Simon was saying, like. And kind of off of Brian's last point, on the wide diagnosis, if I'm trying to see myself more as like a doctor, right? Like I go to someone's house and it's just like, hey, this isn't right. Do you want to fix it or not? No, not interested. Okay. Just letting them know that that's going on, and and this is especially true for me when I'm making changes to the system, other modifications. Hey, there's issues with your ductwork. You know, we're going to do this other stuff, but you know, what are your expectations when we do this new thing? You know, well, we got this hot room over here, and I think when we put this new unit in, that's really gonna take care of that. No, it's not. You know, like just telling them this won't fix that. It's gonna be the same as it was before. It's just a newer box, right? So like, just kind of that doctor mentality, I think for me has been helpful in terms of just getting more comfortable talking with people about this and saying, oh, the reason that room is hot, well, that's because, you know, this is a 3-ton unit and it's only moving 800 CFM of air, which is a 2-ton, you know, so we can fix that. It's going to be, you know, $3,000 or $4,000. Do you want to do that? No, I don't want to do that. Okay, you know, like, just having those tools in my tool belt, feeling really confident about it, and then having a doctor approach. That's kind of been my mindset going into this. So that's kind of how I think about it, and then this is more about how do I actually apply that. And so we talked about we've kind of touched on static pressure. Static pressure is not actually measuring airflow. It's just measuring pressure. Like Brian touched on earlier, a great example is a balloon, a tire. I mean, even a system. If you hook up your gauges to a system that's not running, you're measuring static pressure. It's just pressure that's not moving anywhere. That's basically, yeah. I don't know. I guess we could just call it not moving pressure, and maybe that would be easier because you're like, oh, static pressure, man, that sounds, yeah, that sounds really like complicated. Wow, like that's going to be hard to understand. But it's just like, yeah, I mean, so imagine like the highest static pressure in the world. Imagine you had like an open return coming in the back, it's blowing through, and then in front of the coil, you just had a box with no ducts connected to it, right? Or, yeah, I don't know. I don't know if this would be a perfect example, but what would the pressure in that box be? It's open on one side, and you're pushing a ton of air into it. What would the pressure in the box be? Would it be high or low? It would be high, right? So that's an example of like, think of that as like the worst duct system imaginable, right? Like a really high static duct system is basically just like all the air from the unit doesn't have anywhere to go. And the way you're reading that is by just checking like the pressure in the box. So you're just checking pressure. And then the manufacturer, they're saying these pressures, if you connect this fan to this little dip switch, then at this static pressure, you'll get this much airflow. And Brian, do you want to do?
Yeah, I want to talk about this quickly. So this is a good example of what I'm talking about. So a lot of people will call a static pressure probe a pitot tube or a pitot probe. It is not. Okay, so a pitot is this little guy on the right, and in a pitot you have an open port in the end. So have you ever seen? Has everybody here seen static pressure tips before and what they look like? So you've got, it's a 90-degree thing, and then it's got little holes around the outside, right? It does not have a hole in the end. So this one here does not have a hole in the end, right? Got it? This guy here has a hole in the end, but it's a tube within a tube. Okay, so you have your total pressure connection and you have a static pressure connection. So the static pressure connection is like outside the tube within a tube, and it's only measuring that same thing that the static pressure probe reads. The total pressure connection just goes right up through the center. So it's measuring actual air pressure coming through, velocity pressure. So you point it towards the air, moving towards it, it's getting velocity pressure, but it still has the static pressure as part of it. So when you connect it to a manometer, the manometer just does the math. You connect the negative part to the static pressure connection, you connect the positive part to the total pressure connection, and it does the math, basically just subtracting the one from the other, and it gives you the answer of what the velocity pressure is. Okay, so total pressure minus static pressure equals velocity pressure. You can then take velocity pressure, and by using a conversion chart, blah, 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 math, and the inside diameter of the duct, you can calculate what the actual airflow is. Now, you're not going to do this, okay? I'm not telling you to do this so you can do it, because in residential, no, you're not going to do this test. This is a dumb way to do it. In commercial, they do this all the time. But the point is that you see, if you wanted to actually measure airflow, you would have to use a pitot tube, you'd have to use extra calculations, blah, blah, blah. Static pressure does not measure airflow. It just measures pressure. And like I said before, it's this weird chicken and egg problem. Because in order to know if static pressure means good airflow, you need to know what your airflow is to know your it's this thing. And so you have to refer back to what the manufacturer says in order for our static pressure to actually be able to tell us something about airflow. But what I prefer to do with static pressure is just ignore all that and just say, hey, look, assuming that the system is producing the airflow that it's supposed to, do we have too much friction? And too much friction means I'm going to have high static, right? So we're making some assumptions. We're making a lot of assumptions, but at least it's something, right? Rather than having to do a bunch of math. If you want to know the actual CFM the system is producing, then your best bet is to use a true flow grid. Nowadays, it's like, if that's what you want to do, if that's what you're trying to accomplish, then just use a true flow grid. Otherwise, just look at the manufacturer charts. With modern variable speed motors and X13 motors, if you set up the taps properly, you're going to get pretty close. And as long as everything's the way that the manufacturer made it, you're going to be in pretty good shape. Now the static pressure is basically just to say, my ducts aren't good, my filter's not good, my coil's dirty. That's what you're doing with it, right? You're not really calculating CFM. A lot of what people teach you, especially the fancy folks, Bill Spohn is one who I love, and I've done this class with him so many times. He teaches you how to calculate airflow using static pressure and factory charts and pitot tubes and induct vane anemometers and doing log Chebyshev traverses. And we don't do that in residential. If you were in commercial test and balance, that would all be great. You're not. You're in residential, so you're not going to do those things. You're going to check static pressure to say, is there too much resistance to airflow, right? You're going to use a true flow grid if you want to actually see what your airflow is. Or if you've got something like an evolution, it'll tell you. Like it'll say, hey, here's what your CFM is. Here's what your static is. Great. Then at that point, you don't need any of that stuff. Make sense?
You got a question?
Yeah, well, what's a good static pressure?
What's a good static pressure? We're jumping right to it.
Well, it depends on whatever the fan coil says. So they're rated for different amounts based off of the manufacturer, based off of the model. I know there were some old ones that were as low as like 0.2. A lot of the modern ones are 0.8. So you want to keep it below the maximum. That's kind of the best recommended practice. It's kind of like, do you want to, you're like, well, how fast can I drive my car? That's like, it'll go 100 miles an hour, but if you want it to last longer, you should probably drive it at 60. You don't want to max those RPMs out. So that's kind of the best practice for figuring out where your static pressure should be. Did you have a question, Tony?
Why they have some equipment, they say need the sink tonnage, the sink capacity, 2 ton or 100, or they say this is a low static, but with the sink capacity. It's a low static, or there's a low static.
A low static unit. Why do they say that? It's the same capacity.
Especially in the rear indoor unit.
Oh yeah, like a.
This fan coil is low static, and this one, the other one.
Medium or high static.
Yeah, basically.
The reason is because, like, traditionally in commercial, you could use whatever static you wanted. Basically, you just have to put it. No, it's because you have to consider that in the design, right? So, for example, if you design a unit that's supposed to go in an apartment, okay, and it's a pancake unit, it goes in the ceiling, and it literally there's a duct here, and then there's like 3 ducts that come off here, and it's like boom, 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 that's it. Well, why would you put a much bigger motor in it than you need to put it in, right? That costs more money, and it takes up more space, and so they say, look, for this application, you don't need high static or medium static, just low static, maybe 0.1, right? It's got a little filter, almost no ductwork, and so you have to design for that budget. And this is where, So I'm going to back up again and say, this is why I started by saying NCI and these other organizations that teach design, okay, that's a different thing. We're not going to talk to you about how to design a duct system. We're going to talk to you about, as a technician, what to look for, right? But to your point, you got to know, like, if you're gonna design a space and you have long ducts and you don't have a lot of space to run ducts, so you know they're going to be small ducts, you're probably going to have to use a mid or high static system, right? As an example, look at some of these systems that are like high velocity duct systems, and the name is escaping me now, but some of the most common ones, like Space Pack, where they're designed to run these tiny little ducts off of them, and they run super high static, super high velocity. They're designed for it. They got big old blowers on them, right? But you pay for that in efficiency, right? If you're gonna run a higher static system, the motor has to be bigger. It has to be able to work against more. And so it's gonna be—
It's like, what can it push against?
Correct. And so in commercial, like when we design big HVAC systems in commercial, there's some cases where it's designed to operate at 2 inches of static. It's just designed for it. It's easy, just get a big old motor, right? And you can do anything you want. In residential, the problem is that we only get what we get. They're like, here, it's 0.5, that's what you got to work with. You don't have any options. 0.5, boom, there it is. And so now you have to start with that and build your budgets accordingly. Like, all right, well, my supply ductwork's not great, so what can I do? Well, I can make a really big return and have like a gigantic filter, so at least that way I'm budgeting some here because I know I've got so much used on my supply. So you have to kind of— does that make sense? Right.
Yeah, let's see. Okay, yeah, so here we go. There's your answer, right? I mean, it's going to be written. It's going to be written on the unit, and that's what you're going to be working with. A lot. Yeah. So again, it does matter where you measure. I think that we covered this maybe in the apprentice class or maybe yesterday. Just yeah. It's all going to depend on where you put those probes. So when they ship the unit, they don't know what filter you're going to put on it. So you're measuring, like, here's the filter, here's the unit. You're going to measure like between the filter and the unit. Yeah, I think you have a slide from yesterday with it on, or
just a drawing. Yeah, and again, like the point here is that— oh, hey, I got some old notes here. The point of this is that you do have to kind of know what's shipped in the box. And so I know you guys don't do gas furnaces, but just as an example, in a gas furnace, the coil is separate. It doesn't come in the box. So total external static has to be measured below and above the furnace, so underneath the coil. So it's annoying as heck is what it comes down to. With us, everything is shipped in the box, but there's a caveat. Sometimes they account for the filter that they've shipped with the manufacturer, from the manufacturer, and sometimes they don't. Right? Either way, who cares? You know, measure it on the top side of the filter. That's going to be a much more effective number, because like I said, even though the Bryant controller tells you total external static, it's lying because it is only measuring it at the blower. Right, so it's not total external static, it's blower static that they're giving you. Right, so depending on where you measure, the further you go away from the blower, the lower the number's going to get. Does that make sense? Because you're adding more things. So if I measure under the filter and I measure in the supply duct, I'm going to get a lower static than if I measure on top of the filter. Because the amount of work that you have to do gets more the closer you get to the blower, because there's more friction on both sides, more resistance to the airflow.
Yeah, you can actually measure. You can measure the static pressure drop of a grill, so like a return grill.
Yep.
And if you go through the actual design process, they're like, here's your budget for a return grill. So
yeah, you can budget for grills, ducts, branches, trunks, return trunks, every filter, all of that you can budget out. But again, for a service tech, what we mostly want to know is what's causing the problem. Mm-hmm. Is the static high in the supply? Is it high in the return? Is the static pressure drop high across the filter? Is it high across the coil? That's pretty much it, right? And all of that is contingent on, is the blower giving us enough airflow in the first place?
Yeah. Right? And so it's troubleshooting. It's troubleshooting just like electrical or refrigeration. You kind of just have to know, like, what are the options? What things could be going wrong? It could be, that the coil's dirty. It could be that the filter's too restrictive. It could be the ductwork's bad, right? You kind of have to like build a list of possibilities and then just check each one. Okay, so the basic process. Again, like Brian was saying, the chicken or the egg thing, right? you need to make sure that the equipment is set up for what you're trying to do, right? If it's a 3-ton, you need to set it up for 3 tons of airflow at 350 CFM, whatever that's going to be for you. Find the manufacturer chart. If you're out in the field, I like the Blue On app a lot. I know it just started being like a paid thing, but you can look up manuals and stuff, and you can look up a lot of the fan charts. NCI also has like generic fan table charts that you can use for PSC and ECM motors, and you guys have those. So you can get an idea of where the airflow is, even if it's a unit that is just, you're out in the wild. And again, so here's how you would do it, right? You look up your model number, make sure everything's clean, turn the unit on, check your static pressure. You look up your model number, it's an XY thing, right? You look up your model number, you look up your static, boop, you hit your number. So that's how you check it. So this is the kind of stuff that I have to deal with. You guys don't really have to deal with this, but this is like an add-on, right? So in my market, I have to figure out what's the pressure drop across this coil. Is it normal? Is it abnormal?
The answer basically is, what it comes down to is, when you're selecting a unit, and this comes up a lot, and even with fan coils, is you have to know the application. And in the past, and again with SEER 2, a lot of this has changed, but in the past, you had to know, based on this situation that I'm going to put this air handler in, what do I select? Do I select something that's got a 0.3 rating, or do I select something that's going to be significantly higher than that? And so like a really good example of that, and again, I don't know Bryant model numbers, they may or may not be the same, but a Carrier, their FE air handler and FV air handler line, they are the same. Okay, FE and FV, they would have like the 002 or 003 match, but you could also use the 005 and it would be higher static. You would actually get better airflow out of that at higher static. And so a lot of times you would pick the 002 or 003 because it was smaller cabinet size, it would fit easier, but it would not perform as well when you actually looked at the performance charts. So that's kind of a version in gas furnaces. It's like evaporator coil. So you know what your static pressure budget is, but you have some evap coils with huge static pressure drops and some with lower, and so you have to choose accordingly.
For measuring our the fan performance and the static and all that, can we just measure it? Like for someone like me who's just learning out, would that be something that you would recommend? You use like with my probes off, look on the app, and then see, it'll tell me based off of what I have, if I have good performance or that.
Yeah, I mean that is, yeah, MeasureQuick does work with that. You can connect the manometers. When you're talking about airflow, this part of it, that's where TrueFlow does a lot better. And again, I know you guys don't have that yet, and so we're going to talk just briefly about that and why it is kind of helpful.
Yeah, but you can use just a fan chart. So TrueFlow or MeasureQuick, if you pull it up, they're going to give you like, here's your total CFM, right? But it's not going to show you where the problems are. That's where you would have to go back with your manometer. And so this is an example. You could do this. I did this with the TrueFlow grid. You can do this with just your manometer, and it'll kind of help you find problems, right? So this was a house where this was a 3-ton system, and this guy, he wanted to, he had a room that was uncomfortable, and his unit was old. So he was like, well, hey, like, should I get a bigger unit? You know, the upstairs is always hot. So I was like, well, let me measure the airflow, right? And so this was a PSC blower motor, which means does everybody kind of know what a PSC versus an ECM motor? Does anybody?
It's a non-variable motor, old school motor.
So it just comes on and just runs. So it was 0.59 total external static pressure, which doesn't seem that bad. And then I go through and I have each piece of the system that I can evaluate, right? So the return duct system didn't seem that bad, right? But so what I noticed right away with this is like, okay, so he's got a 3-ton unit, but it's only doing 265 CFM per ton. So he was only really moving like 800 something CFM of air. So he really has like a 2-ton unit. So he's asking me like, do I need a bigger unit? Do I need a 4-ton, right? Well, I'm like, well, the airflow is way off on this thing, right? What if essentially I could get 30% more airflow and use the same size unit? Like, you know, again, it's just kind of like gathering data and putting these pieces together and kind of trying to look at it and say, like, based off of his complaints and his wants, like, what's the best solution for him? Is it going to be a 4-ton unit? Like, is that what he needs? Does he have a 3-ton right now that's working correctly, and it's just not keeping up? Like, or is there something else? You know, so for this one, I mean, he had a huge airflow problem.
So let's stop real quick. So just looking at this, what would you do?
Check to see what's reading out.
Say that again?
Pull it further if you want to see if it goes up. You know, check them, make sure the unit's rated for 0.5 or 0.3 or whatever it's rated for.
The
All
blower
right.
setting? It was just set for high.
So he said first check to see what the unit's rated for, right? Second, let's look at the filter. Go ahead, Jerry.
Yes, it looks like I'd probably go and increase the filter in the return. But on the flip side of that, sometimes you gotta watch out where you do that. You might increase the static on your supply, so.
Correct, because to Jerry's point, this is a key thing here. So when you increase, because you see the static pressure drop across the filter is pretty high. Like, that's pretty darn high for a filter, right? So if you improve that problem and now your airflow starts to come up, when your airflow comes up, your static is gonna go up everywhere else too, right? So even though right now your return might not look too bad, once you get the filter in right, then you may want to adjust the return as well. So go ahead.
So that takes us into fan law 2, right? It's like, oh, okay, yeah, let's put a bigger filter in. What's going to happen, right? What if I take this system from 800 CFM to 1200 CFM? And again, right, like, my perspective on this is like, I want to fix this for him, right? Is just changing the filter going to fix this for this homeowner? Or if I put that new filter in, like, am I gonna create some other problem, right? Or I at least want to provide him with all the information that I can so that he can make an informed decision. So this is fan law 2, and essentially what you can do is, if we know the original static pressure and we know the original airflow, which you can use, get it using the chart, right? You know what unit you have and what speed tap it's on, and you can check your static pressure. So you know the CFM, and then you're like, okay, I want to go to 1200 CFM, right? In my market, we do 400 CFM per ton, so it was 800. Let's see if we can get this thing to 1200. What's going to happen to the static pressure if I do that, right? Because it's going to go up, but how much? Huh?
If you carry it up, power it on 3 times.
Yeah, so let's see. So this is me just taking the supply component. I wanted to see what was going to happen. Okay, if I took this whole system up to 1200 CFM, what would happen? So I take my original static pressure. I had around 800 CFM of airflow. My new goal is 1200, so I put that on the top over there. And then the squared thing really kills you. That's pretty much what you find out, is that any increase in airflow is like squared is bad in math, right? The numbers get big. The numbers get big really fast. So 12 divided by around 800, you get 1.5. You have to square that, 2.25. So, and then you multiply that by your original static, and then that's like your new predicted static pressure at your new airflow. So
Just for the supply.
yeah, that would be just for the supply. So like right now, you're like, that's pretty good, right? 0.11, that sounds nice. But when you do the math, you're like, man, it's gonna go up a lot. And like a 30% increase in airflow is a 50, 60% increase in static pressure. So it's just something to watch out for. And this has happened to me other times where I'm like, I'll change the filter out and I'll check the static pressure afterwards, and it's actually higher, And again, that's why this is like a learning process for me as well, right? I mean, it's just like any other skill that you learn with, you know, electrical stuff. You're like, oh, it's the contactor. You change the contactor. You ever have that, like, that sinking feeling in the pit of your stomach when you realize you were, like, wrong about your diagnosis? You know? And then you start sweating and the homeowner comes out and they're like, how's it going? You know? When's this baby gonna be up and running? You know, and you're like, oh, it'll be just another minute or two. Just had a few other things to check before we get it fired up. And you're like running up to the attic, just dripping sweat, you know, like, so, you know, like, this is not a mistake-free process, right? Like for me, trying to implement this stuff, and especially if you test afterwards, which, yeah, especially if you test afterwards. We'll just jump to the test out afterwards. You know, you find out a lot of things. This is very, like, revealing, right? I mean, this is kind of like me standing up here in front of you in my underwear. So I put a whole new system. I put a whole new system in for this guy, right? He doesn't want to do the whole duct system, so that's kind of on him. But I'm like, I can do this for you. I can do this for you. We can get it right, you know. We can hit what we need to hit. All we got to do is upsize the return duct and put in a big filter, and we're gonna get you there, right? And it did not work out the way that I wanted it to work out, and there's a couple reasons for that. You know, so I started going back and kind of checking through this. What happened? You know, I put a big filter in. I don't know if, like, this is normally what I do. So I'll put, this is a different unit, but kind of the same setup, right? Like, the filters that fit on the back of the cabinets are almost never big enough. Like, you can go through and look. Okay, so this is how I pick my filters, right? So I use, and it's going to depend on whatever kind of, like, model of filters that you guys use. But you can go through and look at the static pressure for that filter at that airflow, right? So I'm like, okay, cool, you know. I'm going to pick this one here, and at 1200 CFM, it's going to be 0.12. Okay, that's pretty good, you know. So I did not hit that. I got 0.155. What happened was there was, like, a beam in the way, so then I had to, like, make my plenum all weird and, like, tape off part of the filter. So like a lot of stuff happened in the field, and again, that's kind of that front end. Like, I needed to do some more planning on that front end of, like, hey, there's a beam right there. Like, what's going to happen when I put this in here, and then, you know, 25% of my filter is not moving air through it. It's just taped off, you know. So I get these readings. You know, obviously my stomach drops, but the homeowner, they don't know anything. It's just airflow, right? I mean, his house is more comfortable. He's like, wow, we can keep this thing at 73 now, and before it wouldn't get below, like, 78. But just going back through on the back end, and some of this is interesting to me as well. I don't know if you have any thoughts on this, Brian. Why the supply plan and pressure didn't work out with the math?
Well, what was it? But what was it before?
So I was supposed to be, like, I ended up with around 1100 CFM total airflow. And at 1200, the predicted was 0.25. And it was, like, beyond that.
Yeah.
So, and also the evaporator coil dropped, like, so I went back through and I picked out a new coil. When I buy a unit, they're like, here's your furnace, here's your coil, here's your outside unit. The one that they wanted to sell me was going to have a 0.33 static pressure drop. And that's you guys know the cabinet sizes, right? Like a B, C cabinet. So I'm like, okay, I want a bigger one that's going to have a lower pressure drop, right? Like, just like a filter, it's the same thing as a filter, right? Like, the bigger it is, the more the air is going to move through it, and you're going to have less of a drop. So I'm like, okay, I want a better one. I'm going to put in this one that's 0.22. Again, why is it 0.28? I don't know. Maybe I should have used, like, a duct transition or something. So anyway, I The homeowner's happy, but I'm not happy. And this is a lot of the like test out on the back end for me. And this is a lot of what keeps me really interested in this job, right? Is like, I just tried something. I thought I knew what was going to happen. And, you know, this is sort of that like, I got all my data, I collected it all, and then I do my tests at the end, and it's like what is happening here? You know? But to me, that's actually kind of exciting, right? Because that's going to take me back in of digging through this process of like going back in the fall and figuring out what it is that caused me to get these results and what can I do to, you know, actually get it right. So I just want to see if you have any thoughts on all that.
Yeah, so thoughts are, again, the point here is, even if you have the best tools, and even if you are measuring static and all this, solving these problems is not easy and has to be done with care. Because just like he pointed out, when you have that square effect, when you increase airflow, you get big increases in static pressure, okay? And so that's also why it's very important that you have a pretty good idea that you've got the right airflow to begin with. For a technician who's not going through and doing all this design stuff, for you, mostly you just need to know that just fixing one part of the equation, like, oh, I'll just put a bigger filter in it, great, that'll solve it. It's not going to be that simple, right? It's not going to be that straightforward. And that to me is the sort of the summary of this. In terms of how you apply fan law 2 and all that stuff, yeah, those of you in this room, any of you who are going to be designing and selecting equipment and trying to provide solutions to clients, you need to be really thoughtful about that and recognize largely what it is just go bigger. You know, like just go bigger. Get your static pressure lower, right? That's a good thing to do. Bigger return, bigger filter, bigger supply ducts if you can, and especially the stuff that's close to the equipment. Try to get it as big and as well transitioned as possible. To your point, almost certainly the reason why you see a higher supply is because of that transition situation there. A lot of times they make assumptions, if you look in the fine print there, that that you probably didn't do. So yeah.
Yeah.
What do we have next? Any questions?
Questions?
Oh,
yeah. Tell me what you got.
Why some why they say sometimes you need return supply, you need to get the same amount, I mean the same CFN and return, take it, the same supply amount.
I'm sorry.
Saying why it has to be equal balance.
Equal the CFN you take in and the CFN return.
Why does it need to be balanced?
I read some information. They say you need to take more return and supply. And some say no, you got to put the same. It's inside CFM.
CFM, or are you talking about duct?
So do you have it, do you either make it balanced, or you're saying that some people say you have to have the returns bigger, right? More return in supply, right? He's saying that some other people say it should be balanced.
Okay, so let me take that one. Okay, so
Yeah.
Let's think of it this way. So like, if I have a pipe, okay, and I put 1 CFM of air in this end of the pipe, how much air comes out of that end of the pipe? 1 CFM. I can't do anything other than that, right? Like, if I put 1 CFM in, 1 CFM is going to come out. That's how that works. So the question is more likely, why do you put a bigger return in a room than you put the supply in a room, right? Okay, that's likely the question. And the answer to that is that it's not like there's a proportionality between the size of a grill or the size of a duct and how much air is going in or out. Within the entire house, the pressures are going to end up balancing, right? One way or another, whether they bring in air from outside or whatever the case may be. A lot of times here, my guess is, do you guys do a lot of passive ducts, a lot of jumper ducts? Like where they're not actually connected back, or is it a little bit of both?
It's a lot, but not, I mean, it doesn't exist mostly we duct everything.
Oh, you do ducted, or ducted returns. Okay, so the fact that the vent is a little bit bigger doesn't necessarily mean that you have more airflow, right? So if you were to take a balancing hood and you were to measure the return and you were to measure the supply, they should be the same, right? Same coming out as going in if they're both ducted, right? They should be the same. That doesn't mean that they're the same size though, okay? And this comes down to the fact that when we're designing vents and duct systems on the supply side, we want there to be some velocity coming out of the vent. Don't confuse that with velocity in the duct. It's two different things. We don't care if the air moves slow inside the duct. When it comes out of the vent though, we want to size that so that way it has velocity so it throws, okay? And this comes down to Bernoulli's principle, which is the idea that, and the best example is, like if you put your hand this far away from your face and you blow, you can feel it here. That's not all air coming out of your mouth. You can tell actually that you can barely blow and still feel it. Like as long as you put your lips close enough together, you can still feel it, right? Well, that's because when you create a high pressure airstream, a bunch of air is entrained into that stream. So most of what you feel hit your hand, it didn't come from your mouth. Most of it came from the sides. And the reason that is because within a high-speed airstream, it creates low pressure on the sides. Have you ever seen that thing where you can use air and blow it up and a ping pong ball will bounce on the top of the air and it'll just stay there? And that's because you have all of this air coming in the sides that's holding it in place, right? That's Bernoulli's principle. That's what we use with supply ducts. We blow air at a reasonable velocity, and it's not, people say throw, right? Like, I'm trying to throw that air across the room. Really more what it is you're trying to mix the air through the room. So when this air comes across the ceiling here, first off, if it runs across the ceiling, it actually sucks itself up to the ceiling a little bit. That's why we blow air across the ceiling, because it creates a low pressure area over top of it, and it kind of runs across the room and down the outside wall. But while it's doing that the whole way, it's pulling air up from the ground, right? We don't want to do that on a return. On a return, we don't care because it's going back into the duct. You don't get that effect. And so because we don't get that effect, we just want it to be low static. And so we make all of them bigger. It's not like you're just making, if you just made one bigger and all the rest of them were the same size as the supplies, well then that one room would have a lot more air pulling in the return. But because they're all bigger, it should still be balanced return, meaning amount of air coming out of the room, amount of air going into the room are the same. Does that make sense? Go ahead.
Yeah, so one of the things I think of on the returns is, like let's compare it to a garage, like cars to airflow. It's like just because you have like let's say you need a 3-ton and you might make your garage for 5. That doesn't mean 5 cars are going to park themselves in the garage. You're still just going to get 3 in there. But go the other way around. Like let's say you have a 2-car garage and you got to park 5. That never works out.
Sure.
So make sure you have enough room.
Go ahead.
Sitting with them, most returns are right, where they by thermostat.
Uh-huh.
Sure.
Yeah, a lot of times people put the
position
return
it
by the
My
thermostat.
assumption is if we have a bigger return, we're going to pull more quicker, right?
If it's bigger in relationship to the other returns in the house, right? But let's say, let's use a ridiculous example. Let's say you have a gigantic return in every single room and gigantic ducts going back to the unit. It's not like just because the ducts are big, all of a sudden magically the unit's going to bring more air back to it. The unit brings the amount of air back to it that it brings back to it, right? And so that's going to be split proportionally, evenly across all of the ducts. Now, if you have a bunch of small ones and one big one, then more is going to come in the one big one because that's static pressure, right? You're going to have a path of least resistance kind of stuff, right? As more air is going to travel down the lower resistance path. But what I'm saying is that oversizing returns, making them as big as you can, is good. But don't make one bigger than the others. You're going to end up with imbalance. And when you have imbalance in a particular room, where one room is positive pressure or negative pressure, either one, then it's more likely to bring in air from the outside, right? So if you have a negatively pressurized room, bedroom, it's very possible that some of the air that's going to come into that room is going to come in from the attic, around the window, everything else, right? That creates a moisture problem in that room. If you positively pressurize the room, okay, that's fine for that room. Some of it's going to leak outside, which isn't great. But then the rest of the house is now going to be under negative. So now the rest of the house, you're always taking it from somewhere. Go ahead.
I think there's a lot of confusion between oversizing the grills and oversizing the ducting.
Right.
Because a lot of times what happens is oh, never put any 12 by 12 or 12 by 12 return drills. But if it's a tiny little room, you run into more balancing issues. If you say everything gets a 14 or everything gets a 16,
Right.
right? It's not going to be balanced.
Right.
You're going to throw off the balancing of each room. So it's fine if you want to give everything 14 by 14 drills, but it size the ducts according to the airflow.
Correct.
Right? It's easier to balance.
Correct.
So,
And that's where what we're learning in humid climates, what we're learning is that balancing the pressures inside of rooms where the doors are closed, okay? So if the doors aren't closed, we don't care. If the door's always open, doesn't matter. But in rooms where the doors are closed, balancing the pressure in that room is a much bigger deal than we thought it was as we've started looking at the data. Because what ends up happening is when you have an imbalance of pressure on either direction in a room, it causes an imbalance of pressure in the rest of the house, which then drives air either in or out of the house. And when that happens in a humid climate, that results in higher moisture in the house, right? Make sense? That's a really big deal to us because even a little bit of humidity-laden air takes a lot of energy to get back out.
So if all the returns are the same, would it open the room or the hose put on the return? Would it tank up the return or?
If all the returns are the same. So the return, okay, here's all I'm saying. The return needs to be proportional to the supply in that room. That's all. The amount of air that comes back out of that return needs to match the amount of air that's going in with the supply. That does not mean that they need to be the same size. Okay, does that make sense? You don't have to have the supply be the same size as the return for the return to pull the same amount of air out of the room that the supply is putting in.
That's why you have to do the calculation.
Correct.
Because you can't put return just like that.
Right.
Or one drill, just like that. You
Right.
calculate how big is the room, how big is the space. So
Right.
what they have in the room too, because sometimes if you make a calculator like, for example, 200, whatever, in that room is the master bedroom, and they have 3 windows. When the sun coming up, you got a lot of heat in that room.
Sure.
You need to increase it. Sometimes they have inside big TV, that's the heat.
Sure.
inside.
And again, so you're talking about, so there's a couple different things. So you have the ACA manuals, right? That's the Bible of how to do this, but it will make it even more practical. You have to design your equipment, which is how much airflow and how many BTUs in and out. Well, again, you guys don't do heat, so out. How many BTUs out that the equipment needs to be designed for the whole structure, right? Then you have your individual room loads. How many BTUs do we need to put in, or to remove, sorry, from each room, depending on its size and the windows and occupants and all that stuff. And then you have your duct design, which is how much air do we need to deliver and remove from this room in order to achieve that level of BTUs, because BTUs ride on the back of air, right? So we bring air in, BTUs, in this case, ride out on the back of that air. And so that's all what we have to calculate. There is no way to say, well, you just put all the same size returns and that's fine. Or you just put all giant returns and that's fine. Or you put all tiny returns, or that's not how you do it. Now, what I advocate for, if you're going in on a retrofit application, is just make them big and put balancing dampers on them. And then you can use the DG8, like we're going to show here, to balance the pressures in the room when the door is closed. Or you can use an airflow hood. Either way, and now you just go, yep, it's what I designed for. Yep, the return matches. Good. And you're going to solve a lot of moisture problems. And that's the main reason. I'm not even that concerned about, a lot of people are concerned about perfect temperature balancing. That's great, sure. Get it within a couple degrees, that's amazing. However you do that is fine by me. But I'm concerned about you balancing the pressures so that way you're not sucking moisture in. Does that make sense? Because that's what for you guys, that's what I'm trying to solve for here. I'm trying to get houses that don't have mold and moisture problems. Because if you solve that problem, sure, you can do a little balancing here, do that there, get it however you need to in order to make the client happy.
The only way to do both, right? Perfect supply air to the room, because customers do complain. If even 2 degrees, some people complain, you walk in this room, it's hot. The only way to fix really, really well-balanced system in terms of supply air to the room, right? To match the load. And to balance, it's like kind of oversized, and then you got balancing in the supply and return.
Correct.
I said that one time and everybody was surprised. But it's the only way, right?
To have balancing dampers on the return duct?
Oh, I mean, if you're gonna match it,
Right.
you can just match this.
Yeah.
You can use the supply and match your return, but it doesn't mean you match.
Or you can just go to jumper ducts and just make those big, and then you're fine too. Which is,
That's what NCI says there. For the first time I ever heard about the big dampers in the return.
yeah.
That was on the course of all now.
Right, but do you understand why that is?
Yeah,
If
yeah.
you have an active, that's why. It's so that you don't end up with positive or negative
Rooms.
pressure in that room of more than 3 pascals. What I want to do now is I want to go ahead and do that before lunch. I want to go ahead and just demonstrate this because it's very simple. This is the DG8 from TEC, and I want to be really clear, there are only a handful of manometers that have this level of accuracy. So you need to be able to measure in the fraction of a pascal. So it's a tiny, tiny amount of pressure. It's kind of like the micron gauge of manometers. This is not the same as your field piece, your utility manometers, all that you use for measuring static pressure. This is to measure pressure imbalances in a space. So you can do things like measuring from the space to a crawl space to an attic, from measuring from outside, and you can get a really good sense of where's your air coming from and where's it going, right? And this is also very helpful within a space, so you can see in relationship from this room to that room, what is the pressure imbalance? Now again, you could do the same thing by taking a piece of toilet tissue under the door, right? You can get a sense of which direction is the air moving, but this gives you a sense of, is it enough to be a problem or not? And the industry standard is, as long as the structure is reasonably well sealed, anything less than 3 pascals of difference is not a problem. Anything more than 3 pascals of difference is something that should probably be addressed, right? That make sense? All right, so just real quick. So this is a picture of the true flow grid. You've probably seen it before. A lot of what we're talking about here with airflow is, some of it is total system airflow. Is the unit producing the air that we want it to produce, right? So in absence of a tool like this, we have to use static pressure, we have to look at blower charts, all that stuff. I'm sure eventually you'll probably have one of these, and this is really great because it can confirm, even if you only have one, you can confirm, is this unit producing the airflow that it should produce? And it works with this little manometer that I just showed you. But then there's the question of each individual room, right? And that's where, using a tool like the DG8 by itself, you can say, look, I don't know necessarily that I have enough supply in this room, but I can tell you whether it's balanced with supply and return by just sticking this under the door. I don't know everything wrong with the house, but I can tell you if the house is pushing air out of the house or it's sucking air into the house, right? And that gives you a sense of where duct leakage can be and a lot of other things. Because again, if you have a house that's under negative pressure, then it's likely that I either have duct leaks in the attic or I have imbalance where I'm pushing air and kind of trapping those boxes of air in the rooms, like Matt was saying, right? And so it gives you another little kind of access point that you can consider. There's also a really neat little card, and I didn't bring one with me, but it's called the roomulator. Do you have a roomulator on you?
I don't know. Let me look and see.
And it's this little card that you hold up against the door frame, and you watch the pressure until it gets to 0 as you open the door. And so based on how big the crack is in the door, it tells you how much additional return you would need or door undercut in order to make the room 0. It's this funniest little thing. So do you get what I'm saying? So basically you're using the door as like a gauge to throttle and say, okay, this is how much more return I need. Okay, good. Now look at the card. Depending on how big the crack was, how big the door undercut. Yeah, this is it. This is like a little. That's literally it, right? And on the back, it has a little chart there
of like how you could fix it. The different.
And again, this is just one. I'm going to talk after lunch. I'm going to talk a lot more about humidity, and this is just one thing to kind of understand what we're dealing with here. Air in and air out of the building is a really big deal to control humidity, and a lot of times when you're chasing problems that are driving you crazy, these are the things you need to know in order to be able to really solve those problems. Because a lot of times we throw dehumidification, fancy equipment at it, and it still doesn't solve it. And this helps you kind of understand it a little more.
Yeah,
right.
More things to just be able to check off, right?
Thanks for watching. If you're willing, give this video a thumbs up and drop us a comment. Don't forget to hit that bell icon to stay updated with all of our future videos. And as a quick reminder, HVAC School isn't just a YouTube channel. Dive deeper with us at our main website, hvacrschool.com. Curious for more knowledge on the go? We've got you covered. Tune into the HVAC School podcast, available on all your favorite podcast apps. And while you're at it, join our thriving Facebook group. Also, don't miss out on our free mobile applications available for both iPhone and Android. We're all about community, for techs, by techs.